Now we consider a case in which the sample size is small, so that the central limit theorem does not apply. We still want to be able to treat the sampling distribution of a mean as a normal distribution, but this means that the underlying population itself should also be normally distributed for this assumption to be valid. The small sample case breaks down into two subcases, where the population standard deviation sigma is known or unknown. If it is known, then we can proceed as in the large sample case, provided that the population is normally distributed. There is no difference in the procedure from the large sample case. On the other hand, if sigma is not known, but the population is still normally distributed, we use the student's t-distribution, just as we did when constructing confidence intervals in the same scenario. Because sigma is unknown, we need to use a sample standard deviation s to compute the standard error for our test statistic. As always, the test statistic is a sample value minus a hypothesis value divided by the standard error. Once we have our test statistic, we compare it to the appropriate value of a t-distribution with n-1 degrees of freedom, where as always n is the sample size. Recall from the section on confidence intervals that for a given significance level alpha, t alpha n-1 is a t-value such that the probability that tn-1 is greater than t alpha n-1 is equal to alpha. The criteria for rejecting h0 are entirely analogous to the large sample case. We just use t alpha n-1 in place of z alpha. As before, these criteria mirror the alternative hypothesis in each case. For example, if a null hypothesis is mu less than or equal to mu naught, then the alternative hypothesis is mu greater than mu naught, so we reject h0 if t star is greater than t alpha n-1, meaning that the sample mean is large enough compared to mu naught to be statistically significant. Similarly, if a null hypothesis mu is greater than or equal to mu naught, then the alternative hypothesis is mu less than mu naught, so we reject h0 if x bar is so much less than mu naught that it is statistically significant, which is equivalent to t star being less than minus t alpha n-1. Finally, for the two-tailed test, the alternative hypothesis is mu not equal to mu naught, so we reject h0 if t star is far enough away from 0 to be statistically significant, where the threshold for statistical significance is indicated by t sub alpha over 2 n-1. As an example, we test the claim of a small college that its average class size is less than 35 students. Here is our sample, and we use alpha equal to 0.02, so our confidence level is 98%. In keeping with the scenario we have been discussing, we assume a population of class sizes is normally distributed, but we do not know its standard deviation. Because the college wants to establish a claim of a small class size, our alternative hypothesis is h1 mu is less than 35, and therefore the null hypothesis is that mu is greater than or equal to 35. Using the sample standard deviation and sample size, we compute the standard error. Then we obtain the test statistic in the same way as always. Sample value minus hypothesis value divided by the standard error. We then obtain the value of t alpha n-1 with n equals 10 from a t-distribution table. For this kind of hypothesis, we need to check whether t star is greater than or equal to minus t alpha n-1, and since it is, we do not reject h0. Even though the sample mean is less than 35, it is not so much less as to be statistically significant, so the college's claim is not substantiated. Now we turn our attention to hypothesis testing for a proportion. If the sample size n is small, then we must use a binomial distribution to compute the test statistic and p-value, since that is a distribution that the proportion actually uses, and under this condition, it cannot be approximated accurately by a normal distribution. However, if a sample size is sufficiently large, then such an approximation is valid, and this is what we will assume. We first consider one-tailed tests. We will see that the process is entirely analogous to testing for the mean. We compute the test statistic in the same way as before, sample value minus hypothesis value divided by the standard error, where standard error in this case is a previously defined standard error of a proportion. Then, as with testing the mean, if a null hypothesis is h0 p less than or equal to p0, We reject H0 if Z star is greater than Z alpha. On the other hand, if a null hypothesis is P greater than or equal to P0, we reject H0 if Z star is less than minus Z alpha, just like for the mean. For the two-tailed test, we use exactly the same test statistic and reject H0 if the absolute value of Z star is greater than Z alpha over 2. Again, the same process as in testing the mean. The only significant change is in the standard error. To illustrate this process, we test the claim that 65% of teenage cell phone users exceed their allotted minutes. The null hypothesis is that P equals 0.65, so the alternative hypothesis is that it does not. We use a sample size of n equals 225 and get a sample proportion of 69%. Note that for the standard error, we use the hypothesis value of a proportion, 0.65, rather than a sample proportion. Then we compute our test statistic in the usual way. With a significance level of 0.05, since this is a two-tailed test, we actually need Z 0.025. Since the absolute value of Z star is sufficiently small, meaning that the sample proportion is sufficiently close to the hypothesis value, we do not reject H0, so our conclusion is that there is not enough evidence to support the claim that the proportion is not 65%.